Welcome. We are looking at multiple driving forces causing fluxes. We looked at two approaches essentially. An approach that involved simultaneous solution of the conservation equations and the constitutive equations as needed. That was one that needed extensive mathematical effort, and the transfer coefficient approach, which does not need so much of a mathematical effort, but it would be applicable only to a small range of situations. And therefore, the confidence level associated with this approach is less compared to the equations approach. However, it's very useful. It gives us a lot, it even gives us insight into the processes, and therefore, we are picking up that approach also. Today, we will continue with the transfer coefficient approach, simultaneous concentration gradient and velocity gradient. The particular example is that of kinetics of enzymes immobilized on a non-porous surface. Okay. I think we did look at concentration gradient, velocity gradient, even in the previous situation when we looked at KLA and so on and so forth. Then we took a slight detour and looked at some even research applications of the principles of transport phenomena, the basic principles of transport phenomena applied to novel research aspects and so on and so forth, even existing research aspects we could use. Throughout the course, integrated, well meshed into the course, we had a lot of situations where you saw applications to industry situations, industry problems, and so on and so forth. Therefore, I wanted to show you even the application even in cutting edge situations, even in cutting edge research, and that is what we saw through the previous few classes. Let's begin the kinetics of enzymes immobilized on a non-porous surface, the transport aspects associated with it, which impinge on the process dynamics itself. Remember earlier in the course when we looked at diffusion back in the second chapter, we considered the situation when diffusion played a major role in determining the rate of reaction. Okay. So, it was something like this. It was heterogeneous situation where you had a pellet and so on and so forth, pellet in an aqueous environment, in a liquid environment and things like that. Therefore, the overall system is heterogeneous. We looked only at the pellet, which is somewhat heterogeneous. However, what I mean by heterogeneous is from the process point of view. You had a solid phase, a liquid phase and so on and so forth, and things coming into the porous pellet. You remember the situation when we looked at an enzymatic reaction occurring inside the pellet. Substrate had to get into the pellet through diffusion, through its various pores, get reacted there, and then the product needs to move out. Okay. So, there is a process of substrate moving in, product moving out, or in other words, there is transport of product in, transport of product out, and then there is a reaction that is occurring. Both these aspects, the transport and the reaction, have different time constants associated with them. The characteristic times could be different, or they could be comparable. So, depending on whether they are comparable or whether they are very different, the kind of process kinetics could be very different. It could either be completely reaction based, or it could completely be transport based, and so on and so forth. We looked at an effectiveness factor that gave us some ideas to what is happening there and so on. We are continuing on the same lines. However, here there is no diffusion inside the pellet, it is something else. Earlier, diffusion played a major role in determining the rate of a reaction that occurred inside a porous spherical pellet. Now, we are going to consider a reaction on the surface of a non-porous slab. There are no pores there. no pores of relevance there. So, we have a non-porous slab present in a fluid, and the substrate is present in the fluid, it goes to the non-porous slab surface, reacts there, and the product moves out. Okay, that is the process here. So, in the presence of mass transport of reactants from the bulk fluid. So, the reactants are moving from the bulk fluid to the surface, they are getting reacted there, and then they move out. So, the assumptions to at least make the problem tractable and to make it meaningful in certain cases. An enzyme is immobilized on a slab that is non-porous, that's the statement of the problem itself. The reaction occurs only on the surface of the slab. Okay. The intrinsic enzyme kinetics is Michaelis-Menten, the liquid kinetics, the solution kinetics is Michaelis-Menten, and therefore, the immobilized constants, the Km dash and V max dash, would be different from the case of Michaelis-Menten, but that is okay, that we already know. The form of the equation would be the same, and we are going to derive an expression for the process rate. Process is the overall thing. The individual aspects that contributed to the process rate, such as transport and reaction, is what we talked about. Here, we are going to derive an expression for the process rate at steady state. Okay, let us begin. This is the situation here. You have the slab. The longitudinal section is going to be a rectangle. You look at it from the end, it is going to be a rectangle, and you have a y dimension that is going into the screen. We are looking only at the x and z dimensions, maybe, yeah. And so, the hashed part is the slab. You have the enzyme that is immobilized on either surface, and you have a certain region which is the conceptual liquid solid film, liquid here, solid here, where the concentrations significantly change compared to the other regions. Okay. So, this region where the concentrations change is the conceptual liquid solid film, similar to the gas liquid film that we already seen. So, the substrate moves in here, the concentration in the bulk could be a constant, and here it drops, it reacts here, the product moves out. Now, let us consider rectangular Cartesian coordinates, because this slab x, y, z is good enough for an easy description of this geometry. So, we will consider that. We are unsure of the kind of flow in the liquid. Okay, nothing is mentioned about it. It could be sloshing around, it could be a nice laminar flow, or it could be even still. Okay, we don't really know. So, to develop a reasonably general solution, let us take it to be undefined, and let us take a transfer coefficient approach. Once we take a transfer coefficient approach, then it becomes simple. You use a different mass transfer coefficient, and that would represent the conditions. How whether we have direct access to it and things like that is another aspect to be considered, totally different aspect to be considered. That may not be so. However, let us take a transfer coefficient approach to represent the flux of the substrate from the bulk to the surface. So, the flux, which is moles per area, moles per time per area perpendicular to the direction of motion, is some Ks dash times a difference in substrate concentrations, S naught, S at the surface. Okay. So, what is this Ks dash, or this it is of the form of a transfer coefficient times a concentration difference. So, you can see the use of a transfer coefficient approach here. Let us call this equation 6.2.2-1. This of course is the flux, as I mentioned. Ks dash is the mass transfer coefficient per unit area, okay, because the area basis is relevant here. So, this is per unit area. So, that is why there is a dash there, and it can be obtained through correlations that are found in the literature. S naught is the bulk substrate concentration in the liquid, S is the surface liquid solid liquid interface substrate concentration. Okay. and the solid liquid interface where the reaction happens. Of course, nothing happens on the other side because there are no pores, but the entire reaction happens on the surface, and S represents that substrate concentration. At steady state, the substrate cannot accumulate at the catalyst bulk interface, right? At the catalyst bulk interface, at the enzyme bulk interface, which is here. Okay, I think this is where our coordinate begins. So, we are looking at the surface here. At this point where the enzyme ends, we are looking at the concentrations, and what it says is at steady state there cannot be any accumulation of either the substrate or the product. So, at steady state substrate cannot accumulate at the catalyst bulk interface. Therefore, the rate at which substrate reaches the interface must equal the rate at which it gets consumed. Okay. That is essential for steady state, otherwise it is not going to be a steady state. So, if we are doing a steady state analysis, if we are forcing a steady state analysis, which is relevant for most of the time by the way, then this condition must be satisfied. Therefore, the rate at which it reaches the surface is a Ks now, S naught minus S. Note that this Ks is different from Ks dash. Ks dash is on a surface basis. Ks is on a volumetric basis, because the right hand side here, which is the Michaelis-Menten reaction, is on a volumetric basis, and therefore, we need the same basis to compare, contrast, manipulate, and so on and so forth. Okay. So, the rate at which the substrate reaches the surface on a volumetric basis, Ks times S naught minus S, equals the rate at which it reacts, because it cannot go anywhere else, Vmax dash S by Km dash plus S, and we are going to call this as an apparent rate V app. Okay. Let us call this equation 6.2.2 dash 2. As I mentioned, Ks is the mass transfer coefficient on a volumetric basis. Km dash Vmax dash are Michaelis-Menten constants modified because of dashed here, because these could be different from the intrinsic or the solution kinetic constants. This is the immobilized case here. And V app is the apparent velocity of the process itself. Okay. We have been doing things with non-dimensional variables. We know that it generalizes solutions to a larger extent, and so let us do that here also. Let us define non-dimensional variables as follows. The substrate concentration non-dimensional variable x as S by S naught, normalized with respect to bulk substrate concentration, equation 6.2.2 dash 3. And let us bring in a Damkohler number dA, which is a mass reaction rate divided by the maximum mass transfer rate, or in other words, the reaction rate, this is the maximum reaction rate divided by the maximum mass transfer rate. It is not mass, let me correct it right away. So, it is a ratio of maximum reaction rate divided by the maximum mass transfer rate. So, we said there are two major processes, one is transport and then the other one is the reaction. So, Damkohler number gives us an idea as to which one is more important in terms of the maximum possible rates that are there. These may not be the rates that are actually present in the particular situation. The particular situation could have influences from transfer, could have influences from reaction together if they are comparable, and so on and so forth. So, this gives us an idea as to, if you consider the extremes in both cases, what would be the ratio. So, that would give us some idea as to what to work with. So, it is a ratio of the maximum reaction rate to the maximum mass transfer rate. The maximum reaction rate, you know, is Vmax dash rate, that is the maximum rate at which it can occur, the Michaelis-Menten kinetics, and Ks S naught is the maximum mass transfer rate, because Ks times S naught minus S is the actual mass transfer rate. When S equals 0, you will have the maximum mass transfer rate. So, you have Ks S 0 in the denominator here, and let us call this equation 6.2.2 dash 4. If the Damkohler number is much less than 1, then the reaction rate is slow in comparison to the mass transfer rate, and the process is reaction limited. Okay. Remember, the slowest step determines the rate, right? So, if the rate of one aspect of a serial process is slow compared to the other, that one is going to determine the overall process rate. So, if the reaction is slow, the process is reaction limited. If the Damkohler number is much greater than 1, it means that the mass transfer rate is much slower compared to the reaction rate, and the process is mass transfer limited. So, the mass transfer rate would determine the process rate. If the reaction is slow, then the reaction rate would determine the process rate. So, that is the meaning of reaction limited and mass transfer limited. Let us define another non-dimensional number that is needed, k dash. It is nothing but km dash by S naught, equation 6.2.2-5. And if we substitute x, the Damkohler number, and k dash into our expression here, it is nice, we do not have differential equations here or as yet. This is our governing equation when steady state occurs, and therefore, we are substituting these variables with the non-dimensional variables. If we do that, we would get 1 minus x by the Damkohler number equals x by k dash plus x equals V apparent by V max dash. Okay. I just thought I will show this to you and then ask you to pause the video here and go from the equation that has been given on with regular variables and replace the non-dimensional variables, see whether you arrive at this answer. Okay, it will be a nice practice. It will also give you some insights as to what is happening. Please pause the video here and go forward. I am sure you would have arrived at this 1 minus x by the Damkohler number equals x by k dash plus s equals V apparent by V max dash. Okay. This is equation 6.2.2-6. How are we doing in terms of time? You are fine. Okay. Few more minutes maybe. So, if you solve these two parts, let us, this is there are two parts to this equation or three parts to this equation, this, and then this. We will take this and this first. 1 minus x by the Damkohler number equals x by k dash plus x. If we solve this, we are looking for x, an expression for x in terms of the other variables. It is quite clear, 1 minus x here, k plus x here, cross multiply, you are going to get a x squared term, okay, and you have x times the Damkohler number. So, it is a classic quadratic equation. Therefore, your solution is nothing but minus b plus or minus b squared plus 4ac by 2a and so on and so forth. That would turn out to be minus, b is minus 1 when you normalize things, plus minus square root of 1 plus 4k dash by beta squared, the whole multiplied by beta by 2, where beta turns out to be the Damkohler number minus k dash plus 1. So, inside the bracket above, we use plus when beta is greater than 0, and we use minus when beta is less than 0. That provides the realistic solution. Now, the process rate, which is given by V apparent, can be found by substituting x. We have an expression for x and we have V apparent by V max equals 1 minus x by Damkohler number or equals x by k dash plus x. Either one should be fine. Let us see what I have used here, and before that we are going to look at our effectiveness factor. We have already seen the effectiveness factor in the case of diffusion with reaction in a porous spherical pellet when in the second chapter. We are going to define an effectiveness factor on the same lines. It is nothing but the observed reaction rate divided by the reaction rate in the absence of mass transfer resistance. Again, observed reaction rate is what we observe. Reaction rate or observed process rate, you could say. A reaction rate in the absence of mass transfer resistance, or process rate in the absence of mass transfer resistance. This is nothing but a conceptual rate, the maximum possible under the given situations, and this you can mathematically get by putting S equals S naught, because the entire substrate being available at the bulk concentration at the interface, or the substrate concentration at the interface being the bulk substrate concentration, is the situation when there is no mass transfer resistance, and that would give the process rate in the absence of mass transfer resistance. 6.2.2-8, and the effectiveness factor can be used to evaluate the effect of mass transfer on process rates, as we have already seen. Okay. We are reinforcing these concepts, which are very powerful concepts, especially in heterogeneous processes. Heterogeneous, it's not the same homogeneous one phase system and so on. Now, if we substitute S equals S0 in 6.2.2-6, which is our regular expression here in terms of the non-dimensional variables, okay. S equals 0 implies X equals 0. Sorry, S equals S0, that gives you the maximum rate. Then you get this effectiveness factor as X by K dash plus X divided by 1 by K dash plus 1. Okay. Again, I'd like you to stop the video here, go back, work this out, convince yourself that this is indeed happening. You don't have to take my word for this. Check whether there are any errors that have crept in here. If there are any errors, let us know in the comment section or the discussion forum, okay, ask a question forum. Right. This is equation 6.2.2-9. Please pause the video. Okay, see whether you spotted any errors here. If you did spot any error, then let us know. When Damkohler number tends to 0, okay, what is Damkohler number? Maximum reaction rate divided by maximum mass transfer rate. X would tend to 1. X is S by S naught, right? So when the maximum reaction rate, hold on, I'll go to the definition and show you. This is Damkohler number, isn't it? Yes. The Damkohler number we defined as the maximum reaction rate divided by the maximum mass transfer rate. So when Damkohler number tends to 0, it means that the maximum reaction rate is much higher compared to the maximum mass transfer rate is much higher compared to the maximum reaction rate. So if you get there, then of course the process is totally reaction limited. You have very high mass transfer rates, so the slower reaction rate will determine the process, and that leads to an epsilon effectiveness factor epsilon g tending to 1. Okay, you can see this here also. You put x tends to 1, you get 1 by k dash plus 1 divided by 1 by k dash plus 1, which is 1. Therefore, when the Damkohler number tends to 0, you get your effectiveness factor tending to 1. What is effectiveness factor? It is the actual reaction rate divided by the reaction rate in the absence of mass transfer resistance. Therefore, you are tending to the completely reaction controlled regime when the effectiveness factor tends to 1. Then you could write from the same equation there, V app is V max dash S0 by Km plus S0. The process kinetics is the same as intrinsic kinetics here, Michaelis-Menten kinetics. Mass transfer does not affect the process rate. There is no scent, or there is no hint of any mass transfer related term here. The process rate is completely determined by the intrinsic kinetic rate. Okay, mass transfer rate does not affect the process rate. Whereas The reverse happens when the Amkohler number tends to infinity. When the Amkohler number tends to infinity, what does it mean? The mass transfer rate is much less, the denominator is much less compared to the reaction rate, and therefore the mass transfer rate is just much slower compared to the reaction rate, and therefore the process becomes completely mass transfer limited. You substitute that, noting that K needs to be finite, you would see that epsilon g, the effectiveness factor, tends to a 1 plus K dash by the Amkohler number. Okay. And the apparent rate becomes Ks times S naught, right? You see this completely mass transfer determined, the apparent rate. Here the apparent rate is completely reaction determined, and there is no trace of reaction kinetics in the process kinetics. Here it is totally mass transfer limited. So that is this analysis comes in very handy in right from analysis to design to even operation at times, and this is a well-known analysis in chemical engineering terms. Here we have applied it to the enzyme reaction situation, that to an enzyme that is immobilized onto a surface of a non-porous slab. I think that's all I have here for today. I think we've been at it for a while now. It's good to take a break. We looked at, in this class, we looked at simultaneous velocity gradient and concentration gradient, and we handled the velocity gradient part of it through a transfer coefficient approach, and got ideas as to what determines the process rate depending on the value of the effectiveness factor. Let us take things forward when we meet in the next class.